In this section, we're going to do some more exponential problems. These will be a little bit different, and you'll definitely need your graphing calculator for these. So, we know for exponential situations, we have y equals a times b to the x. So, for this problem, our population of a town is 1,345 in 2010. That is our initial value, so we're going to have y equals 1,345 times. Now we need to find our b. We find our b by taking 100%, adding 1.5%, which is going to give us 101.5%, and then changing that to a decimal, which is going to be 1.015. So that is the number that we're multiplying here, and it will be to the x power. Now, in this situation, x stands for years. Y stands for population. This is important because they give us that we want to know when will the population exceed 2,000 people. Well, in this case, y is 2,000, not the x. So we're not plugging 2,000 in. What we have is an equation that looks like this. Now here's the problem. Our x is an exponent here, and we do not know how to solve that equation. So at this point, we cannot figure this problem out without our calculator. Whenever you get to pre-calculus, you'll learn how to use logarithms to solve that, but right now, we don't know how. So what we're going to do is we're going to take our calculator, and we're going to go to y equals. And in y equals, we're going to clear out whatever is there, and we're going to type in our equation that we had right here. So 1,345 times 1.015 to the x power here. So we have this equation that we type in. And we're going to make use of our table and our graph for this. So if we want to use our table, we can press second and graph. Now, your table probably looks different. Let me go back and, if you go to second and window, in the table set, yours probably says auto and auto here. So we want to go down here, if it doesn't, and turn this to auto. And then you can pick whatever number you want the table to start at and whatever you want it to count by. Right now, I'm just going to let it stay where it's at. I've changed this to auto. So I'm going to go back to the table. Uh-oh. What happened? Go back to the table. Why is it not working? Okay, I think there's just a glitch in the calculator. So, if I continue going on down, I can see the population here. It's 1980. Here it's 2010. So somewhere between 26 and 27, I know that I've hit the 2,000 mark. So between 26 and 27 years. Now, it asked me when, which really implies what year. The very first year was 2010. So this would be between 2036 and 2037. Maybe the best way to say that would be during 2036, sometime during 2036. So we have to use that table to figure this out. Let's go to the next problem. In 1990, the population of the town was 5,000. In 2018, the population was 6,000. If the population grew exponentially, what was the rate of the population growth? So this is a little bit different here. We know we're going to have y equals a times b to the x. So I know the initial population, I'm going to use that first population in 5,000. So y equals, or in 1990, which is 5,000. Y equals 5,000 times b to the x power. Now, here I don't have enough information to figure out the growth rate right away. But I do know in 2018, the population was 6,000. Now keep in mind here, x is years since 1990, and y is population. Okay, so 2018 is my x, except for I need to do 2018 minus 1990 to find that it has actually been 28 years since 1990. So my x is 28, my y is 6,000. So watch what I'm going to do here. I'm going to plug those things in. So I've got 6,000 equals 5,000 times b to the 28th power. This is a lot like we did with our y equals mx plus b when we were looking for that b value, but the way we solve it is going to be a little bit different. So to solve this, I would divide off that 5,000, which is going to give me 1.2 equals b to the 28th power. Now, we're not really familiar how to get rid of something to the 28th power. We do know if we have something like x squared equals 25, we could take the square root of both sides to get x equals 5. If we have something to the 28th power, what we need to do is take the 28th root. Or the other way we can think about that is raise it to the 1 over 28 power. We will learn more about that in the next section. Right now, just take my word for it that that works. So we've got 1.2. We'll hit the 2 the key. Make sure you put parentheses around your 1 over 28. So when we do that, we get 1.0065323 as our b. Now, that is our b. That is not our population growth rate. So what we have to do is what we were doing on those problems in Part B. We have to take 1.0065323. We have to move the decimal 2 places to make it a percent. And then we subtract 100. So we are going to get 0.653273% growth for our answer here. Okay, let's do some more problems. Alright, so in this case, a scientist begins with a sample of 20 bacteria. The bacteria double every 30 minutes. How long will it take before there are 1 million bacteria in the sample? So, we are going to begin. Y equals 20 is our number of initial bacteria. The bacteria double every 30 minutes, so that means we're going to be multiplying by 2 every 30 minutes. And we're going to put to the x power. Now, something we want to note here, x here is our time, and x is the number of 30-minute time periods. And y is our number of bacteria. So, we want to know when bacteria will equal 1 million. So this is another of those problems where this is our number of bacteria, so it is our y. So we are going to have to use our table or our graph for this. So if we go to our calculator, if we go to y equals, we'll type in 20 times 2 to the x power here. And we can go to our table. And you can see over here, see this is 4.19E7. Let's go on back up some. A million has 6 digits, so probably best right here. Also, where the calculator has reverted to scientific notation here, if you click the over arrow, it'll show you that actual value right here. So I see somewhere between 15 and 16, I have jumped up to 1 million. Now, sometimes I want to be a little bit closer than that. So if I go back to second window, to the table set here, this little triangle TBL, this is delta table, it's a change in our table. If I want to see more numbers in my table, I could count by 0.1 here, and that'll allow me to get a little bit closer. So if I go back to the table, after changing that to 0.1, now I can see it counts by 0.1, 0.2, 0.3, 0.4. So I'll need to go way on up here, and you can see right here between 15.6 to 15.7, I see that that is where I switched to 1 million. Now keep in mind, this is number of 30-minute time periods. So this is not 15.6 to 15.7 hours. If we want to change this to hours, these are our number of 30-minute time periods. So if we take 15.6 and multiply it by 30 minutes, go back to the main screen here, 15.6 times 30 would be 468 minutes. More than likely you want to know how many hours this is. So if you divide by 60, we would get 7.8 hours. Now, this is still, this is still not an exact answer. So let me show you how to find this on your calculator with the graph, because we can get a better answer. So if we go to y equals, and we see that we have 20 times 2 to the x. Let's go here. Let's put in 1 million right here in our y2. Okay. Now we're going to graph this. We're probably going to have to change our window to be able to graph this, because if we graph it right now, I just barely see something over here. Yours may look different. If we go to window, our time period, we're thinking of how long it takes bacteria to double. So I'm going to go from 0 to 24. That'll be a day. Let's count by ones there. And then let's make our y min 0. Our y max, I know I need to go up to at least 1 million, because I want to know when the sample hits 1 million. So I'm going to make this 1,200,000. And then let's count by 200,000. So now if I go to my graph, I can see my exponential function, and then in here comes the line right there at 1 million. So what I'm looking for is this point right here where those two lines intersect. Our calculator can find that for us. So if we do second trace, we're going to pick number 5, which is intersect. And that will show us where these lines cross. Down here it's going to say first curve. You're going to hit enter. It's going to say second curve, and it should jump up to the other graph, and you're going to hit enter. And then it says guess. So when it asks you to guess, you're going to move over here, move your little spider over here close to the intersection point, hit enter. And we can see the intersection is actually at 15.60964. So if you use the graph, you can find the exact intersection point rather than having to sort of guess like we did from the table. Sometimes the guess from the table is good enough. Sometimes you need a more exact answer. So if we had exactly 15.60964, we could multiply that by 30 minutes. Sorry, 15.60964 0.60964 times 30, and then divide that by 60, and we get 7.80482 hours. So it's very close to what we had here, but more precise in this case. So let's continue on. All right, Jennifer invests $5,000 in an account that gets 6% interest compounded annually. How long will it take her money to double? So here, we want to know how long it takes her money to double. Her initial amount is $5,000. We also know she gets 6% interest, so we are going to multiply this by 1.06 to the x power. That's our equation that we're dealing with. So we want to know how long it'll take the money to double. If we take 5,000 and we double it, that's $10,000 there for our y. So in our calculators, what we can do is go to y equals. Let's clear out the stuff we had from before. And we're going to type in our equation, 5,000 times 1.06 to the x power. And then in that second line, I'm going to put 10,000 just so that I can see it on my graph. Okay. So we've got two ways we can look at this. Let's get an estimate using our table first. So if we go to our table, we are still going up by 0.1, but I think it'll work okay here. So if we go backwards a little bit, here between 11.8 and 11.9, I can see that I jump up to 10,000. It's very close to 11.9 because at 11.9 I just had 10,003. So this is a pretty close estimate. It's probably good enough in a lot of cases. If we need the exact value, if they have told us to round to several decimal places, if we go to the graph, notice I don't really see anything, but down here at the very bottom I do see some sort of line. Remember, for our last problem, our y max was at 1,000,000, but really now we just need a little over 10,000. So let's do 12,000. And let's go down here and let's just count by 1,000. So if we graph that, we can see our exponential equation here, and then we should see our line at 10,000. So we want to know where these two cross. So if we do second and trace, we're doing number 5, which is the intersection. Just hit enter for first curve. It's already very close to our guess, so we'll hit enter one more time. And we get our intersection at x equals 11.895661. So 11.895661 years would be our answer there. Now, you probably don't need to be quite that precise in a lot of cases, but the graph does allow you to be a little more precise. Let's look at our next problem. Kaylee invests money in an account that gets 8% interest compounded annually. How long will it take her money to double? Now, this problem looks a lot like the last problem, but it does not tell us how much money Kaylee starts with. However, let me show you something here. Let's say that Kaylee starts with $1. If she starts with $1, we will have 1 times 1.08 to the x power. So if Kaylee starts with $1, then that means that when she has $2, her money has doubled. So if we go to our calculator, and we have 1 times 1.08 to the x power. And let's just use our table on this one. We got second table. and we want to see where she has $2. So if we go back, here we can see that it between 9 and 9.1. So 9 to 9.1 years. We see that her money has doubled. Now, let's see if it matters if we change how much money she starts with. So let's say that now Kaylee has $100. 1.08 to the X value. So if Kaylee has $100, it will take $200 for her money to double. So let's go change our equation over here. Let's go to y equals, we've got 100 times 1.08 to the X power, and we need to know how quick it will double, so we want to know when she will have $200. So if we go to our table, notice here that right here between 9 and 9.1, we have $200. Now, we could go on and try this with $1,000, $500, all kinds of amounts, but what we're going to find is the amount of money you start with does not matter in how long it takes money to double. Rather, it's the interest rate that affects how long it takes it to double. So in this case, if they don't give you an initial amount and they ask you how long it takes the money to double or triple or quadruple, you can just make up an amount for your initial value, and you're still going to get the right answer. So let's look at this next problem. This one is similar to example 2. Jose invests $3,500 in an account with interest that is compounded annually. After 10 years, he has $5,980 in the account. What is the interest rate that the account gets? So what we have here is we know that we have $3,500 initially. We do not know our growth rate, and we're raising that to the X power here. Here, X is years, and Y is our balance in the account. So we know that after 10 years, that's our X, we have $5,980, which is our balance, our Y. So we're going to plug that stuff in so we can find B. So if we have $5,980 equals $3,500 times B to the 10th power, we've set up an equation that we can solve for B. So to solve this, we'll take 3,500 and divide it off. So in our calculator, we've got, let's go back to the main screen, 5,980 divided by 3,500. We get 1.708571429. Keep that whole number in your calculator. Do not round it. Is B to the 10th power. Now, remember, if you look back to example 2, when we had something that's 28th power, we raised it to the 1 over 28th power. So here, if we've got something to the 10th power, we're going to raise it to the 1 over 10 power. So, in our calculator, we're going to take that number we just had, we're going to use it, we're going to put to the 1 over 10 power. And by doing that, we don't round, so we get our B is 1.055026368. And we do not want to give this as our answer because this is our growth factor, it's not our rate. So to make this our rate, we have to move that decimal place 2 places, and then we have to subtract 100. And when we do that, we're going to get 5.502638%. So about 5.5% is our growth rate there. Okay. here's our next one. There are 10 fruit flies in a sample. After 2 days, there are 500 fruit flies in the sample. Assuming that the flies grow exponentially, how many flies will be in the sample after 5 days? You may be tempted here to say, well, 2 days you got 500, then at 4 days you would have 1,000, and then you'd have 500 more after that, so 1,500. That would be linear growth. So for this, you've got to do it differently. So if we start with 10 fruit flies, we've got y equals 10 times b to the x power. We do not know what b is, but we do know after 2 days, which would be our x, that we have 500 fruit flies, which would be our y. So we're going to plug in 500 for our y, and it's going to equal 10 times b to the second power. So we're going to divide both sides by 10 to solve, and we get 50 equals b squared. Now, we need to solve this here, so when we've got that b squared, I'm going to take the square root of both sides. Or you can think this is also to the 1/2 power if you would rather think of it like that, so that it goes along with the other two problems we've done like this. So in my calculator, I'm either going to do the square root of 50, or I could do 50 to the 1/2 power here, and either way, I get that my b is 7.0710678112. Keep that entire decimal, because if you don't, exponential growth, if you're off just a little bit, it's going to increase, your error will increase exponentially as well, and you'll be off by a lot. So, now this time they did not ask us for our growth rate. We could find it if we needed to, but they don't ask us for our growth rate. What we need is the equation, because we need y equals 10 times 7.0710678112 to the x power. So this is our equation here, and we want to know how many flies will be in the sample after 5 days. So we're going to take that 5 and plug it in right here. So we will have 10 times, in your calculator, if we want to use this number right here without typing it in, we can press second and the negative key, and it will put that number in there for us and raise that to the 5th power. And so we get 176,776.6953, which we could round this to 176,777 flies.